Welcome, curious minds, to the deep dive. Today, we're plunging into, well, probably the most famous equation in the world, mc².
Instantly recognizable, isn't it?
Totally. You see it everywhere. T-shirts, mugs, you name it. It's like the symbol for genius, for Einstein, for relativity itself.
It really is. It's treated almost like the final word on, energy and mass.
Exactly. But what if? What if the real story is actually way more complex, more surprising even? When I was digging into our source material for this, my jaw genuinely dropped a few times.
Oh, absolutely. Our mission today really is to take you on a journey with this equation. We want to challenge some of those deeply ingrained ideas that many of us have about it,
Even people with science backgrounds, right?
especially people with science backgrounds sometimes. We're going to unpack its, let's say, true history, look at what it really means in modern physics, and explore why some of the stuff you might have learned. What's considered outdated by a lot of leading physicists now.
Get ready for some aha moments, folks, because this might just change how you see this iconic equation forever.
We're hoping so.
We're going to find out that Einstein, believe it or not, wasn't actually the very first person to write down something very much like mc².
That's a big one.
Huge! And we'll get into why that whole idea of relativistic mass, mass increasing the faster you go is, well, mostly a misconception, a really persistent one.
And something that gets taught a lot, unfortunately.
And maybe most importantly, we need to talk about why nothing can go faster than light, the common explanation. It needs a serious update. It's actually kind of misleading.
It really obscures the deeper physics. Okay, let's dive in.
Let's do it. Untacking the icon. Okay, so first things first, let's rip the Band-Aid off, the big bombshell. Einstein didn't write mc² first.
Yeah, that often comes as a shock.
I know, it sounds almost wrong to say it, given how tied it is to his name, but the sources are pretty clear variations of this idea, this connection between energy and mass, were floating around for, at least 25 years before his big 1905 paper.
That's right. The scientific scene back then, around the turn of the 20th century, was just buzzing. It wasn't static. People were grappling with huge questions about energy, mass, light.
It was a fertile ground for big ideas.
Incredibly fertile. And interestingly, the earliest hints of this mass-energy connection didn't come out of nowhere. They actually grew out of Maxwell's theory of electromagnetism.
James Clerk Maxwell, from decades earlier.
The very same. His equations described light beautifully as an electromagnetic wave. And as physicists dug into what those equations implied, especially about light carrying energy and momentum, they started seeing this link, an apparent connection between the energy of light and something like mass.
So it wasn't just a random guess, it emerged from trying to understand light itself.
Precisely. It shows the idea wasn't some isolated flash of genius, but kind of a logical step stemming from the best physics they had at the time, Maxwell's equations.
Okay, that makes sense. So who was playing with these ideas before Einstein formally put it into his theory of relativity?
Well, there were several key figures. It really highlights how science often works. Lots of people contributing pieces. Henri Poincaré is a major name here.
The French mathematician and physicist.
That's him. Real giant. In 1900, 5 years before Einstein's 1905 paper, Poincaré had written down a version of the mass-energy relationship. He was thinking about electromagnetic energy and how it might contribute to the mass of an object.
Wow. So he was right on the cusp of it.
Very much so. His work showed that this concept, this mass-energy equivalence, was definitely in the air among the top physicists. It wasn't just one person's idea waiting to happen. Multiple people were converging on it.
And there was someone else too, right? Someone a bit more unexpected.
Ah, yes, Olinto di Pretto. Now, this is a fascinating bit of history. He wasn't an academic physicist. He was an Italian industrialist.
An industrialist.
Yeah. And apparently, he published the actual equation, EMC², in a scientific magazine called AC back in 1903.
1903.
Yeah. According to the historical research, yes. It adds this layer of intrigue, doesn't it? It suggests these ideas weren't just locked away in university departments. They were bubbling up in different places, maybe even discussed by amateur scientists or engineers. The intellectual climate was just ripe for it.
That's incredible. It really changes the narrative. What about the other related idea that mass itself might change with velocity? Was that also being discussed before Einstein?
Yes, absolutely. That's another key piece of the puzzle. Physicists like Hendrik Lorentz and J.J. Thomson were deep into studying charged particles, electrons mainly. That was cutting-edge physics then.
Thomson discovered the electron, right?
He did. And as they studied how these charged particles moved and interacted with electromagnetic fields, they started developing theories where the effective mass of the particle seemed to depend on its speed.
Even before relativity provided the framework.
Long before.
Hmm.
Thomson, way back in 1881, was already calculating corrections to mass based on velocity, specifically looking at terms involving velocity squared over the speed of light squared.
1881, that's surprisingly early.
It is, and Lorentz refined these ideas further around 1899. What's really crucial to understand here, though, is that many of these early ideas, both the mass-velocity dependence and the proto-mc² forms, were often built on foundations we now call non-relativistic.
Like Newton's laws, PMV, that sort of thing.
Exactly. They were using the tools they had, like classical momentum, PMV. And while those tools worked incredibly well for everyday speeds, they started showing cracks when applied to things moving near the speed of light, or when considering the subtleties of light itself.
So they were sort of pushing the existing physics to its limits and seeing inconsistencies.
Precisely. It created this conceptual tension. They had these intriguing results like mass changing with speed or energy having an associated mass, but the underlying framework wasn't fully equipped to handle it consistently. It really set the stage for a necessary revolution in thinking,
Which Einstein then provided with special relativity.
which Einstein provided.
Hmm.
But it wasn't born in a vacuum. It built upon decades of work and addressed the very tensions these earlier physicists were uncovering.
Okay, so the origins are much richer, much more collaborative than just Einstein 1905. But this leads to a really critical point. If these early ideas, especially about math changing with velocity, were based on pre-relativistic concepts, how does that connect to the modern understanding? This whole idea of relativistic mass, is it actually right?
Now we get into the heart of the modern debate, and it's a big one. This is where the popular image of mc² really clashes with how many, maybe even most, working physicists think about it today, especially in fields like particle physics or general relativity. There's the physicist Lev Okun from the famous Landau School in Russia.
Landau and Lifshitz, the textbook authors.
That's the one. Okun has been a very strong voice arguing against the common understanding. He basically says the popular conception of mc², particularly the idea of mass increasing with velocity, is fundamentally misleading.
Misleading how? Because it seems so intuitive you go faster, it gets harder to push, so mass increases.
That's the apparent intuition. But Okun argues it's flawed. He challenges this common sense view. He even quotes Einstein's famous line about common sense being the prejudices we acquire by age 18.
Meaning it's hard to unlearn these basic intuitive ideas even if they're wrong.
Exactly. Okun feels this specific idea, relativistic mass, is so deeply ingrained and ultimately incorrect within the full relativistic framework that he uses the phrase, better untaught than ill-taught.
Wow, that's strong. Better to know nothing than to learn the wrong thing.
His point is that learning about relativistic mass creates a conceptual hurdle that students later have to overcome if they go deeper into physics. It conflicts with a more rigorous formulation.
So what's the correct view, according to Okun and others who agree? If mass doesn't increase, what is mass?
For Okun, and this view is very common in modern physics, there's really only one kind of mass for a given particle. It's the mass the particle has when it's at rest, what we call the rest mass, or more formally, the invariant mass.
Invariant meaning.
Meaning it doesn't change. It's the same value for that particle, no matter how fast it's moving or who is observing it. An electron always has the electron's invariant mass. Its mass does not increase with velocity.
Okay, wait. If the mass doesn't increase, why does it get harder and harder to accelerate something as it approaches the speed of light? What's changing?
That's the million-dollar question. And the answer lies in understanding that in relativity, energy and mass are fundamentally different kinds of physical quantities. They aren't just two sides of the same coin.
Different kinds. How so?
Okay, let's break it down. Energy, E, in relativity, is understood as one component of a more complex object called the momentum 4 vector.
4 vector. Sounds like space-time stuff.
Exactly. It bundles energy and the three components of regular momentum, px, pi, pz, into a single entity that behaves properly under relativistic transformations. Because energy is just one part of this 4 vector, its value is actually coordinate dependent.
Meaning different observers might measure different energies for the same object.
Precisely. If I'm standing still and you fly past me very fast, we'll measure different energies for the same moving particle. However, and this is crucial, energy is still a conserved quantity. The total energy in a closed system stays constant, even if it changes form or looks different to different observers.
Okay. Energy. Conserved, but depends on the observer. What about mass, then, this invariant mass?
Mass m. The invariant mass is different. It's defined in a way that makes it relativistically invariant.
Meaning everyone agrees on its value.
Everyone, everywhere, no matter how they're moving. An electron's mass is an electron's mass, period. It's a fundamental property of the particle itself. But here's the kicker, and this often surprises people. Invariant mass is not a conserved quantity in relativity.
Whoa, hang on. Mass isn't conserved. What about nuclear reactions? ECO set. Mass turning into energy.
That popular phrase, mass converting into energy,
Yeah.
is where the confusion lies. It's not that mass itself is conserved, or that it literally transforms into energy. Our source clarifies this really well. It's more accurate to talk about the conversion of rest energy into other forms of energy, like kinetic energy or radiation.
Rest energy.
Yes. Even an object sitting still has energy associated with its invariant mass. That's the E area or Ilsen-So set part. In a nuclear reaction, the total invariant mass of all the particles before the reaction might not equal the total invariant mass of all the particles after.
So mass can actually disappear or appear.
The total invariant mass of the system can change. What is conserved is the total energy. Some of the initial rest energy, tied to the initial masses, gets converted into kinetic energy of the products, or emitted as photons, for example. So energy is conserved, but the sum of the invariant masses might not be.
That is a really subtle but huge difference. So the mass itself isn't turning into energy, it's that the energy associated with that mass is being released or rearranged.
That's a much better way to put it. Energy is conserved, invariant mass is not necessarily conserved in interactions.
Okay, so back to the equation. If mc² is often misused, what's the correct context? You mentioned rest energy.
Right. The fundamental equation linking energy, momentum, and invariant mass and relativity is actually E, P, C, A, M, C, A, M, C, A. Here, m is the invariant mass, p is the momentum, and c is the speed of light.
That looks more complicated.
It is, but it's the full picture. Now, consider the special case where the particle is at rest. If it's at rest, its momentum p is 0.
Makes sense.
So if p is 0, the equation simplifies. E, C, A, M, E, O, O, M, C, A, O, O. Taking the square root, you get E, 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 N, A. Or, as physicists often write it, E, E, O, O, M, C, O, where E signifies the rest energy.
Ah, so mc² specifically refers to the energy an object has just because it has mass, even when it's sitting still.
Exactly. That's its proper, precise meaning in this modern framework. The source argues very strongly that this equation, E0 is mc², is the one people should be thinking of when they talk about the energy locked up in mass, not the generalized E mu c applied loosely to moving objects, which often implicitly brings in the problematic relativistic mass.
It seems even Einstein himself kind of wrestled with this terminology, didn't he? Was he always consistent?
That's another fascinating part of the story. No, he wasn't always perfectly consistent, especially in his earlier work. It shows how these concepts develop. Interestingly, in his original 1905 paper, he didn't actually introduce a single relativistic mass.
He didn't. What did he do?
When he talked about force and acceleration, he found the relationship wasn't simple. He introduced what he called longitudinal mass and transverse mass.
Two different masses.
Yes, depending on whether the force was pushing the object along its direction of motion or sideways to it. He explicitly noted that you couldn't just assign one single value for mass in the FME sense. He saw the complexity right away.
So he knew FMO was breaking down, essentially.
He absolutely did. And later in his life, his views on using the term relativistic mass became much clearer. There's a famous letter he wrote in 1948 to Lincoln Barnett.
What did it say?
He stated very plainly, it is not good to introduce the concept of the mass m, because mo mi arid vkc, the relativistic mass of a moving body for which no clear definition can be given. It is better to introduce no other mass concept than the rest mass.
Wow. So Einstein himself, later on, explicitly rejected the term that's so often associated with his work?
Pretty much. He suggested just talking about the expressions for relativistic momentum and relativistic energy instead, which used the invariant mass m. He saw the confusion the term relativistic mass was causing.
This is huge. If Einstein himself was against it, how did it become so popular in teaching? How does this play out in textbooks today?
Well, the history of physics education is complex. Some influential figures, like Wolfgang Pauli in his 1921 book, did promote the idea of relativistic mass, and that likely helped embed it in the curriculum early on.
So it got baked in early.
It seems so. But on the other hand, other absolutely foundational texts, like the famous Landau and Lifshitz series on theoretical physics, completely ignored relativistic mass from the start. They only ever used invariant mass.
So there was always a divide.
There was. And the trend now, according to our source, especially in more modern textbooks on particle physics, quantum field theory, and general relativity, is increasingly to abandon relativistic mass altogether. They stick to invariant mass and talk about relativistic energy. It aligns with Einstein's later preference and is just more conceptually sound for advanced physics.
It feels like the physics community is slowly course-correcting its own teaching methods.
Slowly is perhaps the operative word, but yes, the shift is definitely happening towards the more rigorous approach.
Okay, so the concept of relativistic mass is shaky, built on older ideas, and rejected by many modern physicists and even later Einstein. This really makes you question the derivations. If the concept is flawed, maybe the ways we derive it are also built on shaky ground.
That's exactly the next place to look. How are these formulas actually derived, and do those methods hold up under relativistic scrutiny?
All right, let's talk about actually deriving EMCR. There's this classic thought experiment, the light in a box one. You hear it a lot in popular science. It seems so simple and elegant.
Oh yes, the box floating in space. It's a very common one. The setup is simple. Imagine a closed box, just floating there, totally isolated.
At rest.
At rest. Then inside the box, a flash of light is emitted from one wall, travels across, and gets absorbed by the opposite wall.
Okay.
The argument goes like this. The light pulse carries momentum. When it's emitted, to conserve the total momentum of the system box plus light, the box has to recoil slightly in the opposite direction.
Makes sense. Conservation of momentum.
Then, when the light hits the other side and gets absorbed, it transfers its momentum back to the box stops moving. The whole system is back at rest.
Right. So where does EMC² come in?
Well, the derivation then uses the energy, E, and momentum, P-E-C, of the light pulse. By carefully calculating the tiny distance the box moves and ensuring the center of mass of the whole system doesn't move overall, you can mathematically derive a relationship between the energy of the light pulse and an equivalent mass, m, it must possess. And surprise, surprise.
It comes out as E.
It comes out as EMCL or EMCL. It looks like a perfectly neat proof. The source even lays out the equations using light pressure, force, distance. It all seems to check out.
But you sound skeptical. What's the catch?
The catch is huge. The entire derivation, while mathematically leading to the right formula, is fundamentally based on non-relativistic physics.
Non-relativistic. How? It involves light speed c.
It uses c, yes, but the core principles it relies on are classical. Specifically, it crucially depends on Newton's third law, action-reaction. The idea that the force of emission and the force of absorption cause instantaneous reactions that conserve momentum in the simple Newtonian way.
And Newton's third law isn't quite right in relativity.
It's not universally applicable in its simple form. This is a shocker for many people. The classical idea of forces being instantly equal and opposite breaks down when you consider the finite speed of light and how information travels.
Wait, seriously, Newton's third law has issues?
In the context of relativity, yes. Imagine two interacting objects far apart. The force from one doesn't reach the other instantaneously. By the time the force signal arrives, the situation might have changed. The simple, simultaneous equal and opposite doesn't always hold.
So the light-in-the-box derivation, even though it gives the famous answer, is built on a faulty assumption from a relativistic standpoint.
Exactly. It's using classical machinery to derive a relativistic result. It's like, using flawed logic but accidentally getting the right answer for the wrong reason. It highlights how easy it is to mix classical intuition with relativistic concepts and end up with something that looks right but is conceptually unsound.
That is mind-bending. A classic proof turns out to be not really a proof in the right framework. Okay, what about deriving the relativistic mass formula itself? mu yields m euro. How is that usually done?
That one is often derived more formally using calculus. Typically, you start with the expression for relativistic energy. E equals g/say, where dg is the Lorentz factor 1 or c, and relate changes in energy to work done, force, and momentum.
So you can mathematically derive it from other relativistic formulas?
Yes, you can perform the mathematical steps, differentiating energy with respect to momentum or relating force to the rate of change of relativistic momentum. The equations work out to give you that expression for relativistic mass.
So the math holds up in this case?
The mathematical derivation itself, starting from accepted relativistic principles like relativistic energy or momentum, is valid. The issue isn't the math, it's the physical interpretation of the result.
What's wrong with interpreting it as mass increasing?
As we discussed, calling this quantity mass, in the same sense as Newtonian inertia, is problematic. Physicist Carl Adler pointed out that while this relativistic mass term is the thing you multiply velocity by to get relativistic momentum, it doesn't behave like a simple, constant measure of inertia.
Because of the longitudinal and transverse mass issue, it resists acceleration differently depending on direction.
Precisely. It's not a single, straightforward measure of inertia. Using the term relativistic mass implies the object's intrinsic stuff is increasing, which isn't the modern view. The invariant mass is constant. What's changing is the object's total energy and momentum, which grow rapidly as velocity approaches c.
Which is why it's being abandoned in favor of just talking about relativistic energy.
Exactly. Advanced texts prefer to use the unambiguous concept of relativistic energy, which correctly captures the total energy, rest energy plus kinetic energy, without introducing a confusing velocity-dependent mass. It keeps the concepts cleaner and avoids implying something fundamental about the object is changing when it's really about its energy momentum state.
These derivations really expose the pitfalls. Getting the formula isn't enough. Understanding the assumptions and the meaning is crucial. It feels like the biggest pitfall, though, the one everyone falls into, is explaining why we can't reach the speed of light.
Yes. The most common explanation. Let's tackle that one head on.
Okay, the big question. Why can't things with mass travel at the speed of light? Ask anyone on the street, anyone who's taken basic physics, what answer do they usually give?
Almost universally, they'll say, because its mass increases as it gets faster, and it would become infinite at the speed of light.
Right. Infinite mass would need infinite force or infinite energy to accelerate, so it's impossible. Sounds perfectly logical. Simple, neat.
Simple, neat, and fundamentally based on a misconception.
Here we go again. What's the flaw this time?
The flaw is that this explanation relies implicitly on the simple Newtonian relationship EFMA. It assumes that force and acceleration are always directly proportional via a single mass term, and that this mass is the thing becoming infinite.
But we just established EFMA doesn't really work the same way in relativity.
Exactly. That simple proportionality breaks down. Force and acceleration are generally not parallel in relativity, and there isn't a single constant m that relates them in all situations. So the entire premise of the infinite mass explanation that EFMA still holds but m blows up is flawed from the start.
So if EFMA is out, how do we describe force and motion correctly in relativity? What's the right framework?
The key is to go back to a more fundamental version of Newton's second law. The relationship F(E)d(P)d(T) force equals the rate of change of momentum. This formulation still holds true in special relativity.
Okay, F(d)P)d(T) is good, but what's P, the momentum, in relativity?
That's crucial. Relativistic momentum isn't just PMV, it's PME is BdV, where m is the constant invariant rest mass, and Gagel gamma is the Lorentz factor, 1/2 of Vc, which depends on velocity.
Right, the gamma factor brings in all the relativistic effects.
It does. Now think about what FdBBT means. You have to differentiate P gum V with respect to time, since gum also depends on velocity, which changes with time if there's acceleration. The differentiation gets complicated. It's not just m times dv dt.
It's a product rule, and gamma depends on V. Yeah, okay, that sounds messy.
It is a bit messy. The source shows the full equation, but the bottom line is FGA MeAV plus GUM. It tells us two crucial things. One, there's no single mass factor multiplying acceleration A, and two, the force vector F is generally not in the same direction as the acceleration vector A unless the force is perfectly parallel or perpendicular to the velocity V.
So pushing something doesn't necessarily make it accelerate exactly in the direction you push, especially at high speeds?
Kind of, yes. The relationship is more complex.
Yeah.
Which brings us back to Einstein's early insight.
The longitudinal and transverse masses.
Exactly. If you insist on trying to write something like ESMA for specific directions, you need those different effective masses. For acceleration parallel to velocity, the resistance is related to dynamic, longitudinal mass.
Yeah.
For acceleration perpendicular to velocity, the resistance is related to dynamic, transverse mass.
Different resistance depending on the direction of push relative to motion.
Yes. And Einstein knew this. He pointed out you can't just define one single relativistic mass for all scenarios.
Is this just a theoretical curiosity, or does it have real-world consequences?
Oh, it has very real, measurable consequences. Our source gives a fantastic example. The bending of starlight by the sun's gravity, a key prediction and confirmation of general relativity.
How does that relate?
Well, calculating how much light bends involves understanding how gravity affects its path. It turns out that a photon moving horizontally past the sun is effectively affected twice as much by gravity as you might naively expect, or as a vertically moving photon would be affected. This extra factor of 2 comes precisely from correctly applying these relativistic concepts of momentum and how force relates to changes in momentum in different directions, essentially incorporating the insights related to those different effective masses.
Wow, so getting the light bending right depends on this more complex understanding, not just simple EOCR or increasing mass.
Absolutely. If you didn't account for this direction-dependent interaction properly, you'd predict the wrong amount of bending. It's a beautiful confirmation that this more nuanced relativistic picture is correct.
Okay, so it's not infinite mass, it's this complex FD-PDT relationship. What does that actually do to the motion of an object under a constant force? If it's not ephemeral, what does its path look like as it speeds up?
Great question. In classical Newtonian physics, constant force means constant acceleration, ESMA. Leading to a parabolic path in spacetime, velocity increases linearly with time.
Like throwing a ball.
Kind of, yeah. But in relativity, applying a constant force leads to a different trajectory. Because of the FDPDT relationship with Panobife, the acceleration actually decreases as the velocity increases. The object keeps speeding up, but less and less effectively. The resulting path in spacetime isn't a parabola, it's a hyperbola.
Hyperbola.
Yes. Mathematically, the equation for position over time changes. Instead of being proportional to the f-tosh, it involves a square root term that describes this hyperbolic curve. And a hyperbola has an asymptote.
An asymptote. A line that the curve approaches but never quite reaches.
Exactly. And in this case, the asymptote for the velocity is the speed of light, c.
Ah, so that's the real reason. The fundamental laws of motion in relativity, described by FDPDT, lead mathematically to a trajectory where the velocity approaches c asymptotically but can never actually reach it.
That's the heart of it. It's not a barrier of infinite mass you crash into. It's the inherent mathematical structure of relativistic kinematics and dynamics. The relationship between force, energy, momentum, and velocity is such that c acts as a limiting speed baked into the fabric of spacetime itself. It's a property of spacetime geometry, not just a property of matter getting infinitely heavy.
That feels so much more fundamental. And elegant, actually.
It is. It replaces a slightly clunky, flawed analogy, infinite mass, with a deep insight into the nature of motion in our universe.
So we've got these much more nuanced, accurate explanations for mc², mass, and the speed limit. But the old ideas, the simpler, sometimes misleading ones, clearly persist. How does this complex reality actually filter down into physics education? What do students typically encounter in textbooks today?
That's a really important question, and the author of our source material actually did the legwork. They surveyed a large number of physics textbooks from different eras and different levels, specifically looking at how they treated mc² and whether they introduced the concept of relativistic mass.
So like a snapshot of what's being taught.
Exactly. Not judging the author's personal beliefs, but seeing what's explicitly presented to students. And the results are, well, illuminating. They show a real split.
A split. So no clear consensus in the textbook.
Not a universal one, no. On one side, you have quite a few classic, influential textbooks that do use both the general EMOB4 formula and explicitly define and use relativistic mass.
Like which ones?
Think of Max Born's relativity book from the 1920s, Pauli's famous text from the 50s, even Feynman's lectures from the 60s, and widely used undergraduate texts like Beiser's Concepts of Modern Physics. They all introduce relativistic mass.
Wow, Feynman too. That's surprising. It shows how long these ideas have persisted in teaching.
It really does. There's a lot of historical inertia.
Yeah.
These concepts got established in the pedagogical tradition, maybe because they seemed intuitively helpful at first, even if they caused problems later.
Okay, so that's one side. What about the other side? Are there texts that follow the more modern invariant mass approach?
Oh yes, definitely. Particularly in more modern books, and those focused on advanced topics like general relativity or quantum field theory. Many of these explicitly avoid relativistic mass and are very careful about the context of EC², usually sticking to rest energy, EMC².
Any examples?
Sure. Modern GR textbooks like Reiter's or Schutz's. Going back further, giants like Landau and Lifshitz in their classical theory of fields, or Misner, Thorne, and Wheeler in their massive gravitation text, they completely avoid relativistic mass. They use invariant mass throughout. Even Einstein's own popular book on relativity from 1916 didn't really use relativistic mass in the confusing way. And Weinberg's Gravitation and Cosmology is another key example.
So the trend in more advanced, rigorous physics is clearly away from relativistic mass.
The trend is strongly in that direction, yes. As you get deeper into the theoretical structure, the conceptual clarity offered by using only invariant mass becomes much more important.
Were there any books in the middle, maybe using one concept but not the other?
Yes, the survey found mixed usage too. Some books might use the mc², often implying rest energy, but carefully avoid defining relativistic mass texts by Schwartz, and Schwartz or Sean Carroll were mentioned. Others might, perhaps confusingly, use relativistic mass, but not emphasize the general mc² equation. David Bohm's text was cited as an example there.
So it's a real patchwork out there.
It really is. It shows an ongoing tension in physics education. How do you balance making complex ideas accessible for beginners versus ensuring conceptual rigor that holds up at advanced levels? Sometimes, the shortcuts taken early on become roadblocks later.
This survey really drives home that point. For someone learning physics, encountering these different approaches must be really confusing. One book tells you mass increases, another says it doesn't.
Absolutely. It highlights that scientific understanding isn't static. Even for something as fundamental as mc², the way we understand and teach it evolves. Concepts get refined, terminology changes. What was once standard might become outdated.
So the takeaway for the learner is be critical, dig deeper.
I think so. Don't just accept the first explanation you hear, even from a textbook. Understand the definitions being used. Be aware that there might be different viewpoints or levels of rigor. It emphasizes that learning science is about understanding the process and the ongoing refinement of ideas, not just memorizing formulas. Even the most famous equation has layers beneath the surface.
It really makes you appreciate that science is a living thing, constantly questioning itself. Even the icons aren't set in stone. Hashtag, outro. Wow, what a journey that was. We've really gone deep into mc², haven't we?
We certainly have pulled back quite a few layers.
We found out about its surprising pre-Einstein history, this whole complex story with Poincaré, de Pretto, Lorentz, Thomson.
Right, realizing it didn't just spring into existence in 1905.
And we tackled that huge, persistent idea of relativistic mass, finding out why most modern physicists, and even Einstein later in life, thought it was better avoided.
Focusing instead on invariant mass and relativistic energy for clarity.
And then the speed limit. Debunking the infinite mass idea and uncovering the real reason the hyperbolic nature of relativistic motion baked into space-time itself via FDPTT.
A much more profound and accurate picture.
It really shows how these concepts we often take as simple starting points are actually incredibly rich, complex, and have evolved over time.
It's a perfect example of how scientific understanding refines itself, striving for greater precision and deeper consistency, even with its most famous symbols.
So here's a final thought to leave you with. If the most famous equation in science, mc², has this much nuance, this much ongoing debate about its interpretation and how best to teach it, what does that tell us about the nature of scientific knowledge itself?
Maybe it tells us that true understanding isn't about finding simple final answers that fit on a t-shirt.
Yeah, maybe it's more about the process, about constantly questioning, digging deeper, refining our models, and learning to be comfortable with the beautiful, sometimes baffling complexity of how the universe actually works.
It suggests the journey of discovery is never really over. There are always more layers to peel back.
So what other scientific truths that you think you know might be waiting for their own deep dive? Something to ponder.
Keep questioning, keep exploring, and definitely stay curious. You never know what you'll uncover.